Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
QuantumLaserPointers.com.
When you look at the history of quantum physics, it's gone through a number of revolutions. When I was a graduate student in the Dark Ages, people were still kind of worried about the foundational issues, but at a very fundamental mathematical level. And people thought of experiments which are sort of thought experiments, Gedanken experiments, to try and illustrate some of the fundamental behavior of quantum matter. Anton Zeilinger is the person who actually carries these things out, as we'll hear. I've known Anton a very long time. A number of episodes, which I will recount to anybody later on during the drinks. You must ask him about the Dalai Lama's visit to his laboratory at some point. But in particular, when Slovakia joined the European Union, we'd had an agreement that we would do all sorts of things to celebrate that. And a group from Vienna and a group from Slovakia decided that they would send a greeting from one part of the border to the other to celebrate the accession of Slovakia. And a group from Vienna sent off this quantum key distribution, quantum cryptographic message, and it was decoded at the other end. And I'm aware that we have diplomats present. And the message essentially from the Viennese side to the Bratislava side said, "Welcome back." Those of you who know anything about the Austro-Hungarian Empire will realize. Anton has distinguished himself for a wide variety of experiments, initially with neutrons, and then with highly correlated beams of light at the quantum mechanical level, often using parametric downconversion. His famous experiment in the end of the 90s on quantum teleportation was a landmark within the field. He's gone on to work on ways in which information can be carried quantum mechanically. Famous third man experiment of key exchange involving the sewers of Vienna. Lots of things we can relay to you at another time. When the Institute of Physics looks back on its growth, we now got, 34,000 members. And with members from all over the world, it was really very fitting that we had an international award, a premier award to recognize excellence in the physical sciences. And I think it's really fitting that our first awardee of the Newton Medal, our international medal, is Anton Zeilinger, a citizen of the world, one with whom the UK quantum optics community have enjoyed a very happy and very long relationship. So we all look forward to hearing Anton's lecture as the first Newton lecture of the IOP. So Anton, welcome.
Thank you very much, Peter, for your kind introduction and for the precise memory concerning what I call the Slovakia event, where we were in the car together, actually, crossing the border. Sehr verehrte Frau Botschafterin, dear President of the Institute of Physics, my dear colleagues, I'm really very grateful for having been chosen for some reason, which is strange to me, the first recipient of the Newton Medal. This is quite a distinction. I highly appreciate that. Today I have been told to give the first Newton lecture, and I choose the title Quantum Information and the Foundations of Quantum Mechanics. This is a title which would have been impossible the years ago when I started to be interested in the foundations of quantum mechanics. What you see here in the picture is a telescope. It's a telescope on one of the Canary Islands, on the island of Tenerife. And I will mention more about this kind of experiments later on. Let us go back a little bit to the beginning of quantum mechanics. The birth of quantum physics is often said to be the year 1900, when Max Planck explained the blackbody radiation with his assumption of quanta of light, of the quantum of action. I recently discovered that this dating might be incorrect. Actually, 1.5 years before, Max Planck had a quantum of action written down in a paper. At that time, he did not appreciate its importance, but in 1900, he also did not appreciate its importance. So the foundation of quantum mechanics, one might argue that it started actually in June 1899. I wrote down 4 names here who are not often mentioned: Kuhlbaum, Lummer, and Pringsheim and Rubens. These were the people who actually did the experiments on blackbody radiation. You see a picture, which this is a recreation of the experiments back then. The blackbody investigated is here. So this is a hollow cylinder which can be heated from the outside, and one studies the light coming out here. And to explain that light, Max Planck had to assume that light is quantized, that it comes in indivisible quanta. I want to jump right into the matter of my talk. In a sense, early quantum physics was signified by the fact that many of the interesting things people predicted, they could not do at that time because of technological problems, technological limitations. And the 2 fathers of quantum physics, Heisenberg and Schrödinger, had their part in predicting some of these phenomena using Gedanken experiments, using thought experiments. Here's Heisenberg's microscope of 1928, where he shows that you cannot measure the position of an electron without changing its state by a reflection of photons. And back here is Schrödinger's famous cat paradox, where he couples the states of a cat, live or dead, to an radioactive atom. The radioactive atom can, after some time, be in a superposition of decayed and not decayed, and therefore, if quantum mechanics is universally valid, the cat is also in a superposition of dead and alive, which clearly doesn't make any sense. And there are scores of papers where people argue why it doesn't make sense to talk about cats being in a superposition of dead and alive. The way we read such papers, where people in general propose some limits for the validity of the laws of quantum mechanics, the way we read them is simply to find out that while the papers are certainly correct, what's the way around? What is the experimental way around the argument? I will mention a little bit more in that direction. The next step in Gedanken experiments was the famous Bohr-Einstein dialogue in the late 20s and early 30s. Here's a picture from the dialogue, the two-slit experiment. This picture was made by Niels Bohr himself in a write-up of 1948. The dialogue was essentially, philosophers might forgive me for making these statements so short, was essentially that Einstein's position was that physics is about what is, about reality out there, while Bohr's position was that physics is about what can be said about the world. And I will come back to this dichotomy a couple of times during my talk. This drawing was made by Bohr, and I really like it. Bohr was a theoretician, as you know, but you see he drew the screws here. So he knew that details in experiment are very important. I don't want to go into too much details. The question raised by Einstein is, you can do this experiment, which is easily understood with intensive light. You get dark and bright fringes. You can do this experiment with individual photons, and then the obvious question is, what happens? It turns out that with individual particles you will get also the stripes, and furthermore, you then can raise the question, which Einstein did, was which of the two slits does a particular particle go through? And if it goes through, say here, how does it know whether the other one is open or not? Because it has to know that to show the interference pattern. The modern way, and Bohr's answer was to say that you are only allowed to talk about features of the world like a path taken if you really do the experiment, which allows you to determine what happens. A further jump from Bohr into the beginning of some of these fundamental experiments. This is 1975, experiments done by my supervisor in Vienna, Helmut Rauch, who started the field of neutron interferometry. You have this kind of devices made of perfect crystals. The size here is a few centimeters. And you split an incoming beam of neutrons onto different trajectories and bring them on superposition again. This kind of experiments is now everyday fare with atoms and molecules and so on. But back then it was quite unique. And I have a feeling that in terms of enclosed area, this is still the record for interferometers, probably. So these first experiments were done in Vienna, actually, in 1974, 1975. And here's one example of one of these early experiments. It's what's called the spin rotation of a spinor rotation of a neutron. The simple point is that, you know, if I stand here and if I turn around once, then the universe is the same again. Not much change. Not if I were a quantum object. If I were a quantum object, then I have to turn around twice to be the same, to have the same universe again. And here are the interference fringes seen in this kind of experiment. The important point in terms of intensity here is that the intensity in this experiment is so low that when you detect one neutron, this next neutron, which will be detected, has not been born yet. It is still sitting in its uranium nucleus waiting for fission to happen. So these are really low intensity experiments. Here's an experiment done in 95 by my student Birgit Dopfer with individual photons. I mentioned before that this Einstein question, what happens to an individual particle? Here's an experiment where you create pairs of photons. You use one photon as a trigger, which tells you that the other one is on its way. And here are the interference fringes, these stripes seen by Birgit Dopfer. The important point is the intensity here. The maximum is 120 in 60 seconds. So in other words, this means that most of the time the apparatus is empty and sometimes you have a photon coming through. The solid line is theory from first principles, no free parameters except the total intensity. A question to be raised is how large can objects become to show this kind of phenomenon? And I mentioned before that I personally expect that there is no limit. The limit is only a question of money and of experience, of experimental experience. I'm sure we will learn to see these things for incredibly large objects. Here's an example with fullerenes, carbon-60, carbon-70. So the question is, if things become very massive, will we enter a classical world on itself? The answer in my eyes is no. If they become complex, the answer is also no. Temperature might be different, because temperature provides a way for a system to talk to the environment. Here's a sketch of these early experiments with fullerenes, also done in Vienna in 1990. In 2000, 10 years wrong, sorry. In 2000, the experiment with these large buckyballs, not a two-slit, but a grating, a multi-slit grating system shown to the lower right here. And these are the interference fringes observed, just the same kind of thing as before with the photons, but now for carbon-60 or carbon-70 molecules. The interesting point to be mentioned here is the difference between experiment and theory. This is theory from standard optics. This is experiment as observed, and it seems that experiment is better than theoretical prediction. The peaks are higher and more well defined. The reason is Casimir interaction. The reason is the fact that the molecules passing through the channels of the interference grating experience the fact that the walls are there, and through interaction of virtual particles, and therefore they experience a phase which is position dependent and leads to this kind of thing. So that is one case of a famous saying by Richard Feynman, who said that yesterday's sensation and Casimir interaction was a sensation. There was a Nobel Prize given for the Casimir interaction. Yesterday's sensation is today's calibration and tomorrow's background. In our experiment, the Casimir interaction is a background. So I raised the question, how large can objects become to show quantum interference? Now, the problem is decoherence. The problem is the fact that a quantum system might interact with the environment and that way lose its coherence. One experiment we did is a decoherence by emission of thermal radiation. You have your incoming fullerene heated up to quite high temperatures. The temperatures here were of the order of 4,000 to 5,000 degrees Kelvin. It's quite hot. The question is, why do the molecules not fall apart at that temperature? The answer is that cooling by emission of radiation is a faster process than breaking apart. Okay, so they cool down, but they still emit photons, and these photons, here are the wavefronts, emit photons, and these photons can tell the environment where the fullerene is. They give the information about the path, just as we said before in the Bohr-Einstein dialogue, and therefore you have loss of quantum coherence. So decoherence can be seen or understood as a flow of information into the environment, and in this kind of experiment one gets very detailed understanding of the mechanisms, quantitative understanding, which allows one to predict by simple scaling in size and temperature that decoherence will not be a serious problem for molecules as large as small viruses, even at room temperature. So if you go to larger objects, there's lots of possibilities. There's no serious limit. So these are the interference patterns for increasing temperatures. Here we start at some low laser power, and then when we heat up, we lost the interference pattern. Okay, so where's the status of this kind of experiments? The record in terms of mass is this molecule. It's a carbon-60 with additional fluorines sticking out, carbon-60, fluorine-48. The record in terms of size is this molecule, azobenzene, which was done by Markus Arndt and his people. He's doing these experiments now alone, just about a year ago. This molecule is already very large, 3.2 nanometers, and it shows perfect interference. So there's nothing which makes quantum coherence go away if a molecule becomes floppy like this kind of thing and might twist around and vibrate in all kinds of things. A very interesting new development in going to larger objects is where people in different places try to put mechanical levers, small mechanical levers, into quantum states. This is a picture taken by people in my group. These experiments are done by Markus Alstenmeier and his students and postdocs. This is a picture of small mechanical levers made of silicon, and what you see here are patches of basically anti-reflective coating. This will be the mirrors in cavities where where one tries to couple these cavities to quantum states of the radiation field, and maybe see some entanglement either between photons and these mechanical systems, or between mechanical systems themselves. We talk here about very large masses already. We talk about masses of the order of 10 to the 20 atomic mass units. So this would be a huge step in mass compared to what we have these days. Back to fundamental questions. Here's a picture of fullerenes as classical objects. A tunneling microscope image of these molecules sitting on a surface, and here you see them localized on a scale which is much, much smaller than the scale between the interference paths I showed you before. So the question is a fullerene a classical object or a quantum object? And the simple answer is it depends. The question whether something behaves classical or quantum, as Bohr always said, depends on the experiment you do. The experimenter decides whether a system is classical or quantum by choosing the apparatus. There is no objectivity. So the same piece of apparatus in one experiment can be on the classical side, and on the other, in another experiment, can be the quantum object. So this also means that there is no border between the quantum world and the classical world. It depends on your experiment. Here is a picture taken in an American parking lot. As always, our friends across the pond are far ahead of us. They have. This is a picture Charlie Bennett gave me. They have obviously quantum cars, which are able to leave a parking lot in a superposition of two possibilities. And this picture proves that they exist, because a quantum car you cannot observe while it passes through. Right? Okay, so far a single particle interference, and now we come to the second part of my talk. It's entanglement. This is a very famous paper, 1935, published by Einstein, Podolsky, and Rosen in the Physical Review. And this paper itself has an interesting history. First, it was never seen by referees. At that time, it was just accepted away. And as some of you might know, as soon as Physical Review started to send Einstein's paper to referees, he never sent them a paper again. Okay, that's a very good. That's a position which would not be possible these days anymore. But then, at that time, it was possible. Second interesting point is that this paper was only quoted about once per year until the mid-60s. And now it is quoted about 200 times a year. So that tells you something about the importance of citation indexes and Hirsch factors or whatever, you know. It took 40 years until this paper was appreciated. It's now the most frequently quoted paper by Einstein. In that paper, for those who don't know the story yet, in that paper Einstein, Podolsky, and Rosen identified that you can have quantum systems which are connected in such a strong way that the quantum states cannot be separated into individual states, meaning or implying that if I do a measurement on one of the systems in the state, it instantly collapses, changes the quantum state on the other system, no matter how far it is away. Einstein didn't want that. He called it, in a derogatory way, spooky action. Schrödinger in the same year coined the notion entanglement for the situation, and he said, and I tried to symbolize this here a little bit. He said that the interesting thing is that you can have two processes, namely the measurements on two systems, two entangled systems, where each one is completely random. Schrödinger talks about expectation catalogs not being defined, but as soon as you measure one, the outcome on the other measurement is well defined. Schrödinger says that this is a situation you cannot have in classical physics, where you have well-defined expectation catalogs for joint observations, but undefined for individual observations. Actually, it turns out that this came out very shortly after the Einstein-Podolsky-Rosen paper, that Schrödinger was worrying about this already for a couple of years, as one knows now. Here are a few remarks about the situation. Einstein, Podolsky, Rosen themselves introduce the notion of elements of physical reality, saying that upon measurement of one system, I can predict with certainty what the corresponding measurement on the other system would give me, and therefore it makes sense to introduce elements of reality corresponding to this property. And they argue that these elements of reality are not contained in quantum mechanics, and therefore quantum mechanics must be incomplete. Famous is the last sentence of the paper, where they say, while we have thus shown that the wave function does not provide a complete description of the physical reality, we left open the question of whether or not such a description exists. We believe, however, that such a theory is possible. Now we know that at least the last sentence of the paper is definitely false. About the rest, one can argue that's a question of philosophical position. But the last sentence is certainly false. Here is Bohr's answer in the same year. Bohr never wrote papers in a very clear way, so if you ever read Bohr, read him a couple of times. It takes a while, and he supposedly once said that when people complained about his writing style, that he should write more clearly, he said that, why should I write more clearly than the way I think? Okay, there's a point to that. Bohr, in his answer, which is quite interesting, basically says that physics is about what can be said about the situation, and what can be said about the situation depends on the context of the complete experimental setup. An interesting statement was given by Perez in 2003, and I say this here because I like it very much. This statement here, quantum states are not physical objects. This is quite important. They exist only in our imagination. This is on Bohr's side. In summary, the question raised by EPR, can quantum mechanical description of physical reality be considered complete, has a positive answer. However, reality may be different for different observers. So we see here already reality is at stake. Now, this is a Newton lecture. What would have Newton said to this kind of question? There's a letter from Newton to Bentley, probably a precursor of this car company or whatever. Bentley, dated February 25, from the winter 1692-3. He clearly talks about gravity here. He says, it is inconceivable that inanimate matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact. In entanglement, we seem to have something like that. And then he says that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. And I simply took the liberty to replace gravity by entanglement. Okay, and then you can adapt the same sentence to describe the situation of entanglement, where in entanglement we seem to believe that there is no mediation of anything between the two observations at the time of the measurement. Now, all this, I mentioned to you before that the Einstein-Podolsky-Rosen paper was only quoted about once a year for the first 30 years, and this changed in 1965 when John Bell, Irish physicist, did something very interesting, and he showed that the Einstein-Podolsky-Rosen idea, if carried through, this final sentence would lead to a contradiction with quantum mechanics. The situation is simply that you have a source which puts out pairs of particles, here as photons, where both photons are either horizontal or both photons are vertically polarized, and you do measurements on the polarizations on both sides. If you measure the same polarization, you get perfect correlations, but if you measure at a small angle with respect to each other. You don't get perfect correlations anymore, but statistical correlation, and it turns out that these statistical correlations are stronger than what a local realistic picture would allow you. And that is the essence of Bell's inequality. What does local realistic mean? Einstein locality, in the words of Einstein, is the assumption that for the relative independence of spatially distant things, A and B, this idea is characteristic. An external influence on A has no immediate effect on B. And realism, the measurement results are determined by properties the particles carry prior to and independent of observation. There's an interesting situation for 3 particles. I mentioned before that if you have 2 particles and for small angles you get a contradiction, you get stronger correlations than what a realistic model a local realistic model would allow you to do. For 3 particles it's even more funny. If you have 3 particles, 3 photons say, and you measure the polarizations with the 3, then there are situations where upon 2 measurements, when you predict the 3rd one, a local realist would predict an exactly opposite state from a quantum mechanics. And and this again raises the old question of the debate between Einstein and Bohr. Is physics about what is, or is physics about what can be said? If physics were about what is, then this kind of situation, and also the Bell situation before, leads into troubles. It leads into at least the conclusion that the local realistic position is not possible. If physics is just about what can be said, then there's no problem at all. But then we have to answer what is reality. I will come back to this at the end of my talk. Just to make one point clear, which is important, the difference to classical correlations. There's a beautiful paper by John Bell from 1980 with the title Bertelsmann's Socks and the Nature of Reality. There's a strange title of a physics paper. Bertelsmann wrote it to explain, as he says, to philosophers what the interesting issue here is. There's a physicist called Bertelsmann, a real physicist. He still exists. He's in Vienna. He's a colleague of mine in Vienna. He worked with John Bell for a long time in CERN in Geneva. And Bertelsmann, Reinhold Bertelsmann, his first name is Reinhold. When we go through the kind of formative years, some of us decide to do something to protest against the world. And Bertelsmann decided to never wear socks of the same color anymore in his whole life. So he still does. He's now obliged to do it. He still does it. You know? And so when you see what Bell said, when you see Bertelsmann coming around the corner, he really looks a little bit like that. And when you see one sock, you know that and if you see that the sock is pink, then you know definitely that the other sock is not pink. Now this is trivial because you know that Bertelsmann pulls always different socks on in the morning. So that's a very trivial thing, nothing interesting. If these were quantum socks, as Bell argues and shows, if these were quantum socks, then the assumption that they would have these colors before you look at them would be wrong. Or more precisely speaking, before the first observer looks at them. So quantum socks, Bertelsmann would have to pull on blindfoldedly in the morning. Otherwise, they carry information. It's not so trivial. It's a little more complicated. But that's just to stress again and again. You write even in books by famous physicists, you read that the situation is as simple as this, which is simply wrong. Now, experiments. Interestingly, this is one of the funny coincidences in science. Bell wrote his paper just when experiments were about to be possible. Just about at the time of the discovery of the laser. I mean, what would have happened if he had written the paper much earlier? I don't know. It's a very interesting question. So people started to do experiments on entangled photons, on photon pairs. The first experiment was done by Friedman and Clauser. Then there was a beautiful series of experiments by Aspe in the 80s and some more recent experiments closing loopholes. I don't want to go into these details. That's the graph from the first experiment. You create your entangled photon pairs. You send them to two analyzers, polarization analyzers. You measure the transmitted photons. In more recent experiments, the setup, this is an experiment we did in Innsbruck a while ago. The setup looks much more difficult. You have a polarizer. You measure both polarizations. You have an electro-optic modulator to change the polarization at the last instance before you measure it, because that way you can exclude any unknown communication. But these are details and not so important for our discussion here. Here's a picture of the way how simple these experiments are today. So what you do is you use a non-linear optical crystal, pump it with some laser. This is a blue laser here. In some experiments, we did it with a simple laser pointer. So it's very easy now. We create pairs of photons, couple one of the photons into this glass fiber, the other one to another one, and send it to distant places. These experiments are so simple now that we do them regularly in student laboratories. And many people are talking about producing this for schools, but nobody has done it yet. Then, my title, I talk about quantum information, the foundations of quantum mechanics. The big surprise was in the early 1990s for me and for many people working in the field. I'm sure it was a big surprise for you, Peter, also, and for other people. You know, when somebody asked me 20 years ago what this is good for, what we are doing here, these experiments on the foundations of physics, my answer always was, honestly, that this is not good for anything. This is useless. This is just part of the identity of humans to be curious, to do experiments, to want to try to find out how the world works, just like listening to a Beethoven symphony. But this has changed, to my big surprise. There were people who started to have ideas how this might be used and applied in experiment. The essential concept is the quantum bit, the qubit, introduced by Ben Schumacher. It's the quantum superposition of two states, 0 and 1, of a bit. Quantum superposition could be, for example, the two paths in the double-slit experiment. And you can have entangled qubits and so on and so on. And it's obvious if you encode information that way, then you can do much more than what you would be able to do in a classical situation. Here's an example. Quantum cryptography picture. This is actually a picture put together the way it is by Physics World, who are an IOP journal. This is an article coming up in the next issue in July by Markus Aspelmeier and myself about this kind of things. So you create entangled photons, which are perfectly correlated in polarization, for example. Which means that if you measure many pairs of photons, you get the same random sequence on both sides. This was an idea proposed by Arthur Eckert in 1990. It was actually, as far as I know, the first paper in quantum information which made it into Physical Review Letters. That's quite interesting for the field. Anyway, Arthur Eckert was a student of yours, right? That's right, yeah. So you get random sequences of numbers, which you see a graphical representation here. And then what you do when you want to encode a message, for example, this picture of the Venus of Willendorf, an effigy found about 100 kilometers from Vienna. You mix them bit by bit. Here's the encrypted message, and because the original is random, this is secure against eavesdropping, but the receiver can decode it. Actually, the reason why we chose the Venus of Willendorf in these experiments, I have said that many times, was because we wanted to have a symbol which is certainly not a military symbol and which is Austrian. So this is an Austrian figure. It's most likely not a military symbol. It's actually it's actually the first time, and probably the only time, as far as I know, that an unclad person was imaged in Physical Review letters. And nobody complained. Okay, anyway. The status of quantum cryptography is rather mature. There are companies offering simple systems, actually not based on entanglement, but that's not so important. And I just want to tell you that there is a European network where also some British colleagues participate. It's called SecuQC, and we will run a test of a quantum cryptography network in Vienna in October this year. So on 7th or 8th of October. So this will be quite interesting, where we show that different hardware built by different groups can connect to each other and exchange quantum cryptographic keys. Here, teleportation, already mentioned by our chairman. The idea proposed by Bennett, Balzac, Repot, Joseph Perez Wutas. And this is actually an interesting a situation to talk about with respect to the Bohr-Einstein debate. The situation is simple. We have Alice who wants to teleport a quantum state, a quantum system in an arbitrary state. This is the general qubit. And the way she does it, over to Bob, the way she does it is that Alice and Bob share an entangled pair, and Alice projects these two particles on an entangled state, on a so-called Bell state. And here's the state which comes out. I apologize to the non-physicists for these equations here, but the basic point is that upon measurement here, you will have a state over at Bob's side, which can have four different manifestations, which contains already all information which is contained in the original. And then in order to finally get the original state, one has to know what the measurement result for Alice was and do a unitary operation here, but that's not so important. Now, there's a lot of debate about how does the information teleportation go from A to B. It does not seem to follow a certain path, but it disappears here, that the original loses its property, and it reappears here. Now, if one uses this kind of language, one is already, in a sense, on the realist side. If you're on the side of Bohr, then all that happens is that what you can say about the situation depends on what the measurement result is here, depends on new information. And if that information changes, then what you say about the situation, i.e. the quantum state at the receiving situation, has to change. So for a strict Bohrian, in a sense, there is no problem here. It's just a question of language. Here's a picture of the 6 people who proposed the the teleportation, and this is obviously Schrödinger's cat or whatsoever. But that is not so important. Here's a picture of an experiment done across the river Danube 2 years ago, teleportation from one side of the river to the other one. I just want to come back to the interpretive question once more, talking about this experiment. Where the idea was put forward by Asher Perez in 2001. The idea simply is that you take two entangled sources, and you submit, or you don't submit, one from each of the pairs to a Bell state measurement, to project them on an entangled state. Then what happens is that you can view this as teleportation of this state over here or this state over here. What happens is that two, say, photons, which never interacted, become entangled. So far, so good, and that has been seen in experiment. But the interesting question now is that Alice might receive these two photons at the time when Bob has done his measurements already, when all the records are written down. And Alice can decide by what measurement to perform whether these records here correspond to photons which are entangled, which have been entangled with each other, or whether the same records already written down, correspond to entanglements between 1 and 2 and 3 and 4. But these are two completely different physical pictures which are mutually exclusive. As we like to say that entanglement is there's a monogamy of entanglement. You cannot have both entanglement with two different systems at the same time, a perfect entanglement. So what happens? How can the decision of Alice what to measure at the later time change the physical story behind here, the physical interpretation? Now, what actually happens, and the way to see this is that the events here, the events just happen. You measure the photon, the event just happens, there's some classical record. But the meaning of the event is the complete story, the complete interpretation depends on actions which might lie in the future. So again, to me this underlines once more that physics is not about what is. It's not about what is out there, but it is what can be said about the situation. What can be said about the situation might depend on actions which are in the future. This is an experiment which is going on now in our lab. Xiaosong Ma, a student of mine, is trying to do this experiment where we decide at the last instance, when these have been registered already, randomly whether Alice projects these on an entangled state or measures them separately. Okay, just to really confirm that what's going on is what we expect. Now, how large distances can we see entanglement? There's a series of experiments going on, some of it in collaboration with people, including Rarity in Bristol, at the Canary Islands. So these are some of the Canary Islands. We do entanglement distribution and similar experiments between the two islands of La Palma and Tenerife off the west coast of Africa. Now you can imagine that this is a nice place to do experiments. You work at 2,500 meters above sea level, and when there is no fog, you work all night to collect your photons. The distance between these two islands is 140 kilometers, and here's some pictures of the setup. That doesn't tell you too much. That's the sending station where you have two lenses with which you can send two photons over to a receiving station, optical ground station over there on the island of Tenerife. Now that's a picture of a beacon laser here. The receiving station is a telescope operated by the European Space Agency, a telescope which was built for the specific purpose of communication with satellites. And therefore, it has two important features. Firstly, it can follow a satellite with high precision. And secondly, it can go all the way down to the horizon, which usual telescopes cannot do. So we point the telescope horizontally over to La Palma. This mountain is El Teide, the highest mountain of Spain. There is an interesting connection to Newton again, since this is the Newton lecture. On La Palma, the sending station, there's a cluster of telescopes. It's actually very interesting. On Tenerife, you have telescopes which are essentially for observing the sun during daylight, but Tenerife is highly populated, so the telescopes for night observation are on La Palma, 140 kilometers away, and there is one of the group of telescopes is called Isaac Newton Group, actually run by this country, as far as I know, by the United Kingdom. This is the Isaac Newton Group, and our sending station is a little bit over here to the left, up on the same mountain. Here's a picture of the kind of experiments which we did. It's a paper which is about 1 year old, just to show you what happens. That is a satellite picture So what you see up there are ocean waves, very long wavelength ocean waves. And for example, you create pairs of entangled photons. One is measured locally. The other one is sent via these telescopes over to the other station to create quantum cryptography keys, for example, or to test entanglement. Now, this kind of experiment does not test quantum non-locality because the first photon is measured instantly. Now, this year we are doing an experiment where the first photon is delayed so much that the two stations are actually space-like separated. This experiment will start in a week from now, and it will be quite interesting again. The future is experiments in space. We have a program with the European Space Agency to actually build sources for satellites and send photons down to 2 different locations on Earth. The situation is that this kind of project is scientifically accepted. We just need the smallest amount of money, like about 50 million euros, which for space people is actually a small amount. It's not very big. So we are optimistic that we will be able to put this together in a large international collaboration. I want to come back to the fundamental question. From Bell's inequality and the experiments, we know that local realistic theories are inconsistent with both the predictions of quantum theory and with experimental observation. So the question is, which assumption is wrong? Is it locality, or which would mean that maybe one can work with non-local realistic theories, or is it realism, which means that one might be able to work with local non-realistic theories, whatever that might mean, or is it both? Now, this again was just a philosophical question, very much as the original Einstein-Podolsky-Rosen question was just philosophical until Bell came along. This was just a philosophical question until Tony Leggett in 2003 proposed what he called a crypto non-local hidden variable theory. It's a theory where you again do measurements on 2 photons over a large distance, where you measure some parameter here, and you have some outcomes, 1 and -1. And but the assumption now is that the physical states emitted are actually statistical mixtures of sub-ensembles with definite polarization. Okay, and the new thing is that Leggett allows the measurement result on one side, say A, the measurement result on one side, depend not only on lowercase a, which is the setting of the measurement apparatus, say the orientation of a polarizer on A, but also the setting of the measurement apparatus on the other side, and instantly. One might think that way one can do anything, but that's not quite true. Leggett was able to show that one can construct a theory which explains all existing experiments and obeys the no signaling condition, namely that you cannot send signals faster than the speed of light. The new thing in these experiments is that Leggett developed an inequality, a generalized kind of Bell inequality. The new thing is that in these experiments, one has to measure not only linear polarization, but one has to go out of the plane of linear polarization in the Poincaré sphere. This is a Poincaré sphere, left, right, horizontal, vertical polarization. One has to measure correlation between linear and elliptical polarization. And lo and behold, when you do this, you arrive. This is this angle phi is the angle by how much you go out of this plane of linear polarization. These are the measurement results, and here's the limit of Leggett's theory. So lo and behold, this theory is also in conflict with quantum mechanics and in conflict with experiments. One point is that this kind of experiment would not have been possible like 10 or 20 years ago, because you need much higher quality of the entanglement. So this is one of the things made possible by the progress in quantum information. Now, what are we left with now? What does the situation mean? So, the issues at stake is whether the locality assumption is true or not. It seems to be not relevant. The question is to which extent can we talk about a realistic picture of the world, or one possibility would be that the world is totally deterministic, or that we have actions back into the past, or that our simple logic is wrong, and so on. I put big question marks here because I keep saying that we need a philosopher. We need someone like what Immanuel Kant did for classical physics, for quantum mechanics. But maybe I'm too romantic in that expectation. I want to quote Leggett again. He said that the incompatibility between quantum mechanics and these realistic theories has little to do, in his opinion, and I share this opinion, with locality, but it has much to do with objectivity, which is his name for realism. And the questions which we can raise now is questions like, how strange must a non-local theory be to agree with quantum mechanics? There is one, namely Bohm theory. Then an interesting research program might be to classify non-local theories by all kinds of features they might have and see whether we can do new tests. A very deep question which I have been fascinated for a long time is can we construct a test theory of quantum mechanics like we have it in general relativity? It doesn't seem to be possible, and the point might be that quantum mechanics is too airtight. And the more practical question is to look for multi-particle generalizations of non-local theories. Just to show you what the experimental experiments are, which people have gone through, and to see what we might do in the future. This is these are pictures from this upcoming article in Physics World, and they did a very nice job drawing them. This is the Bell-type experiment where you measure linear polarization on 2 photons. Then this is the 3-particle correlation experiments where you measure on 1 photon linear polarization, on the other circular polarization. And this is the Leggett-type experiment where you measure on one side linear polarization, on the other one elliptical polarization. So this covers pretty much all bases you can do with 2 or 3 photons. And it seems that one has to go to higher photon numbers to ask new questions. So the question is how to go to higher photon numbers, and an interesting line is integrated microoptics, which is being pioneered, among other groups, by O'Brien in Bristol, was in Australia before. That's a picture of a controlled NOT gate he built in glass fibers, microoptics. And there are interesting questions one can ask. One can create and measure multi-photon states now with in this kind of system, I hope with higher purity and so on than one would expect. The idea is to integrate this with new sources and with new detectors. I personally expect that it will be quite interesting to investigate higher dimensional Hilbert spaces. One can ask fundamental questions. Already, as some of you know, with Hilbert spaces of dimension 6, new things come in. The number of mutually complementary bases is an open question for 6 dimensions. And there are interesting questions, like there's a beautiful paper written by Conway and Cochin. Conway is the person who invented the game of life, which they call the free will theorem. The free will theorem says that basically, if one can assume that the answer of an elementary particle upon certain measurements is random, is completely random, they say if they have free will, then the experimentalist must also have free will. That's quite an interesting statement. But there are experiments to be done, namely experiments in entanglement in higher dimensional Hilbert space. And I'm sure that once these experiments are done, they will lead to new applications in quantum information. So we are at an exciting point right now, where the technology people developed to handle more complex systems just for quantum information might lead to new fundamental questions. Here's an artist's rendering of a 8-photon entanglement, which I call the quantum crab. Looks like a crab. It's the artist's picture how to imagine that you can have 6 quantum systems perfectly correlated with each other. I actually like that picture. I think it's beautiful. So I want to come to an end. I don't have a watch, Peter. I think I should come to an end. I want to come to an end. I should not stop without mentioning quantum computation, but I don't want to go into details here. There are different paradigms of quantum computation. One is where you have a quantum computer which provides a unitary evolution of an input state, and you get some output state as the result. And there's a new scheme started by Niller, Flamm, Milburn, and proposed by Rausendorf and Priegel, where you start with a sufficiently complex state, and where subsequent measurement, one measurement after the other one, provides the computation, which is a very different paradigm than all other computation schemes. But I don't want to go into the details here. I also don't want to go into the experimental details. That's how a typical optical table looks like. This is a small section of this kind of experiment, but it's all easy. You know what each screw means. This is standard fare. I just want to say a little bit about the future of this quantum computation stuff. I know there are quantum algorithms, and the first quantum algorithm proposed was actually by David Deutsch. The first algorithm which can be more efficiently solved on a quantum computer than on a classical computer. Here's an example of the Grover algorithm, which might be interesting for the non-physicist because it shows the potentiality. The challenge is, the question is, you have a phone book, telephone book, and if you know the number, if you know the name of a person, you can easily find out the telephone number if you know the alphabet, right? If you don't know the alphabet, you have a problem. But if you know the alphabet, you can easily find out the telephone number. But other way around, if you know the telephone number, it's very difficult to know the name of the person. This is the problem of searching in an unsorted database. And it turns out that with a classical computer, you have to essentially look through the whole telephone book to find the right name. On the average, you have to look, and sometimes you are successful, sometimes you are not. So on the average, you have to you have to make n over 2 lookups, where n is the number of entries in the telephone book. So if there is a phone book with 2 million users, a classical computer has to check 1 million entries. A quantum computer only has to check square root of n entries, which for 1 million entries is only 1,000. So that is a significant progress. But I want to speculate a little bit about the future. And what I show you here is called Moore's Law. Gordon Moore was the founder of Intel, or one of the founders of Intel Corporation, the company which creates these computer chips. And Moore found by a simple observation of the technology that the number of elements on the computer chip doubles every 2 years initially, and then he revised it to every 18 months. So in terms of the physics, it simply means that the individual devices get smaller, the individual elements get smaller and smaller. So you have less and less atoms, less and less electrons needed to encode 1 bit. And one can estimate that on a time scale of roughly 20 years, at most, actually, if one extrapolates now, one arrives at a situation where 1 bit of information is carried by 1 electron anymore in this kind of circuits. And then we are at the quantum limit. So it will happen. So therefore I wrote down here, quantum information technology will happen by extrapolation. Now, extrapolation can bend off, we all know this, but it will happen some days. And I also would like to predict that quantum computers will not be built to solve exotic algorithms, but they might even be used in everyday life. I'm very optimistic here, but I'm optimistic because I believe that the problems of decoherence and so on can be overcome. Now, let's go back to the philosophical question once more. The question, how real is reality? Do objects exist if nobody looks? Is the moon there when nobody looks? You know, there's this famous story that supposedly Einstein asked Bohr, do you really believe that the moon is not there when nobody looks? And Bohr is said to have answered him, can you prove to me the contrary? Which is very wise. It's actually the point that physics is about what can be said about nature rather than about what is. Now, I might speculate a little bit. We have this old evolution in our philosophy, but also in Eastern philosophy. That's one of the things I learned in my discussion, since you mentioned the Dalai Lama. The old discussion between the two extreme camps of idealism and realism. In modern language, the relationship between information and reality. And it seems, since, in my opinion, quantum mechanics is about what can be said about the world, information seems to be very important in the universe. It may be even constitutive to the universe, whatever that means. And that has been said. I couldn't avoid to put that quote down. That has been said actually in St. John's Gospels. The first sentence says, in the beginning was the Word, whatever that might mean in that connection. Now, there is an article written by Hans Christian von Baer, which you find on the net, about some of these musings. But I want to conclude with a sentence of Newton, which I really like. You know, he wrote, I keep the subject of my inquiry constantly before me and wait till the first dawning opens gradually, by little and little into a full and clearer light. Maybe this happens someday with these issues about reality and information in quantum mechanics. This is my last but one picture, my group in Vienna. This is one of the big fortunes of my life, and not only of my life, is if you look at the picture, then this is by far the oldest person on the picture. And it's really a big joy to work with these young people all the time, with these young, bright minds who are full of fantasy and ideas. And since I noticed that there are some young people, some students here, my last picture is an advertisement, together with Harald Fritsch from Munich, who is an elementary particle physicist, theoretician. We are organizing a school in Bad Honnef in Germany in September, which is called Foundations of Quantum Physics. This is an experiment, elementary particles together with quantum mechanics. We want to see how it goes. And if students here are interested, this is a physics school. If students here are interested, just look it up on the website. And there are still some openings. So if you want to come, just write an email to this website and with a little motivation why you want to come, and I'm sure you will enjoy it. Thank you very much for your attention. People predicted they could not do at that time because of technological problems, technological limitations. And the two fathers of quantum physics, Heisenberg and Schrödinger, had their part in predicting some of these phenomena using Gedanken experiments, using thought experiments. Here is Heisenberg's microscope of 1928, where he shows that you cannot measure the position of an electron without changing its state by a reflection of photons. And back here is Schrödinger's famous cat paradox, where he couples the states of a cat, live or dead, to in radioactive atom. The radioactive atom can, after some time, be in a superposition of decayed and not decayed, and therefore, if quantum mechanics is universally valid, the cat is also in a superposition of dead and alive, which clearly doesn't make any sense. And there are scores of papers where people argue why it doesn't make sense to talk about cats being in a superposition of dead and alive. The way we read such papers, where people in general propose some limits for the validity of the laws of quantum mechanics, the way we read them is simply to find out that while the papers are certainly correct, what's the way around? What is the experimental way around the argument? I will mention a little bit more in that direction. The next step in Gedankenexperiments was the famous Bohr-Einstein dialogue in the late 20s and early 30s. Here's a picture from the dialogue, the two-slit experiment. This picture was made by Niels Bohr himself in a write-up of 1948. The dialogue was essentially, philosophers might forgive me for making these statements so short, was essentially that Einstein's position was that physics is about what is, about reality out there, while Bohr's position was that physics is about what can be said about the world. And I will come back to this dichotomy a couple of times during my talk. This drawing was made by Bohr, and I really like it. Bohr was a theoretician, as you know, but you see he drew the screws here. So he knew that details in experiment are very important. I don't want to go into too much details. The question raised by Einstein is, you can do this experiment, which is easily understood with intensive light. You get dark and bright fringes. You can do this experiment with individual photons, and then the obvious question is, what happens? It turns out that with individual particles you will get also the stripes, and furthermore, you then can raise the question, which Einstein did, was which of the two slits does a particular particle go through? And if it goes through, say here, how does it know whether the other one is open or not? Because it has to know that to show the interference pattern. The modern way, and Bohr's answer was to say that you are only allowed to talk about features of the world like a path taken if you really do the experiment, which allows you to determine what happens. A further jump from Bohr into the beginning of some of these fundamental experiments. This is 1975, experiments done by my supervisor in Vienna, Helmut Rauch, who started the field of neutron interferometry. You have this kind of devices made of perfect crystals. The size here is a few centimeters. And you split an incoming beam of neutrons onto different trajectories and bring them on superposition again. This kind of experiments is now everyday fare with atoms and molecules and so on. But back then it was quite unique. And I have a feeling that in terms of enclosed area, this is still the record for interferometers, probably. So these first experiments were done in Vienna, actually, in 1974, I highly appreciate that. Today I have been told to give the first Newton lecture, and I choose the title, Quantum Information and the Foundations of Quantum Mechanics. This is a title which would have been impossible the years ago when I started to be interested in the foundations of quantum mechanics. What you see here in the picture is a telescope. It's a telescope on one of the Canary Islands, on the island of Tenerife, and I will mention more about this kind of experiments later on. Let us go back a little bit to the beginning of quantum mechanics. The birth of quantum physics is often said to be the year 1900, when Max Planck explained the black body radiation with his assumption of of quanta of light, of the quantum of action. I recently discovered that this dating might be incorrect. Actually, 1.5 years before, Max Planck had a quantum of action written down in a paper. At that time, he did not appreciate its importance, but in 1900, he also did not appreciate its importance. So the foundation of quantum mechanics, one might argue that it started actually in June 1899. I wrote down 4 names here who are not often mentioned: Kuhlbaum, Lummer, and Pringsheim and Rubens. These were the people who actually did the experiments on blackbody radiation. You see a picture, which this is a recreation of the experiments back then. The blackbody investigated is here. So this is a hollow cylinder which can be heated from the outside, and one studies the light coming out here. And to explain that light, Max Planck had to assume that light is quantized, that it comes in indivisible quanta. I want to jump right into the matter of my talk. In a sense, early quantum physics was signified by the fact that many of the interesting things...
Yes. Anton has distinguished himself for a wide variety of experiments, initially with neutrons, and then with highly correlated beams of light at the quantum mechanical level, often using parametric down conversion. His famous experiment in the end of the 90s on quantum teleportation was a landmark within the field. He's gone on to work on ways in which information can be carried quantum mechanically. Famous third man experiment of key exchange involving the sewers of Vienna. Lots of things we can relay to you at another time. When the Institute of Physics looks back on its growth, we now got, 34,000 members. And with members from all over the world, it was really very fitting that we had an international award, a premier award to recognize excellence in the physical sciences. And I think it's really fitting that our first awardee of the Newton Medal, our international medal, is Anton Zeilinger, a citizen of the world, one with whom the UK quantum optics community have enjoyed a very happy and very long relationship. So we all look forward to hearing Anton's lecture as the first Newton lecture of the IOP. So Anton, welcome.
Thank you very much, Peter, for your kind introduction and for the precise memory concerning what I call the Slovakia event, where we were in the car together, actually, crossing the border. Sehr verehrte Frau Botschafterin, dear President of the Institute of Physics, my dear colleagues, I'm really very grateful for having been chosen for some reason, which is strange to me. The first recipient of the Newton Medal. This is quite a
Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. This convenient and affordable double-slit laser was designed for personal enjoyment and education.
QuantumLaserPointers.com.
When you look at the history of quantum physics, it's gone through a number of revolutions. When I was a graduate student in the dark ages, people were still kind of worried about the foundational issues, but at a very fundamental mathematical level. And people thought of experiments which are sort of thought experiments, Gedanken experiments, to try and illustrate some of the fundamental behavior of quantum matter. Anton Zeilinger is the person who actually carries these things out. as we'll hear. I've known Anton a very long time. A number of episodes, which I will recount to anybody later on during the drinks. You must ask him about the Dalai Lama's visit to his laboratory at some point. But in particular, when Slovakia joined the European Union, we'd had an agreement that we would do all sorts of things to celebrate that. And a group from Vienna and a group from Slovakia decided that they would send a greeting from one part of the border to the other to celebrate the accession of Slovakia. And a group from Vienna sent off this quantum key distribution, quantum cryptographic message, and it was decoded at the other end. And I'm aware that we have diplomats present. And the message essentially from the Viennese side to the Bratislava side said, "Welcome back." Those of you who know anything about the Austro-Hungarian Empire will realize